Okay, so my name is Blažević, and I'm gonna talk about something that's provisionally called language Haskell. If you have any familiarity with the ecosystem, that's just language something, which already appears in like dozens of packages. And typically that's just the abstract syntax tree of the language parser and pretty printer. And somehow Haskell was missing from that list, so here it is. At the moment, it's only a candidate package, which you can look up. So if anybody is offended at my use of the namespace, speak up and I'll think of some other name. Anyway, which Haskell you might ask, and it's actually almost all syntactic extensions of Haskell 2010. And furthermore, it's maximally flexible so that it can be extended further. So what's it all for? It started 4.5 years ago, actually, as a proof of concept of composable grammars, and the proof succeeded. Yeah, it's definitely composable. Not that anybody cares particularly. It might become an alternative to the old Haskell source extensions package, which hasn't been maintained for several years now. I hope it could be a base for new experiments in the Haskell space and also somewhat outside the Haskell space. Pie in the sky idea that if we ever get a new Haskell standard, this would be a pretty good starting point for the language grammar. Because if you look at GHC grammar, it's just one big ball of all the extensions, which are really difficult to separate. In practice, it's been most useful so far to generate bugs in GHC. And most importantly, I was having fun with it. What it isn't for, probably will never be, it's not likely to ever become efficient because it's kind of clashing with the other goals of composability and extensibility. The grammar is using parser combinators. It's not generated parser, doesn't have separate lexical layer. I'll show you later why, but the AST is at least twice as large as it could be. It won't have good error messages because when you have a composable grammar and that tries to be really strict and prescriptive as to what's allowed, that's kind of opposite of what you want to do if you want good error messages. Then you want a relatively lax grammar, and when you get syntax tree, then you check it afterwards and report, yeah, that's a good idea, but maybe for some future extension. Unfortunately, even though it's pretty small, it wouldn't be good to teach compiler techniques because I may have got carried away with the use of type-level programming. So yeah, it's not a good code to throw a beginner in. I have to tell you about dependencies because they matter in the design. So apart from parsers, which was originally released by Edward Kmet, all of these are mine. Monoid subclasses you may be familiar with already. It's just a library of mathematical structures that lie between semigroups and groups. And it turns out that there are things there like factorial semigroups and cancellative semigroups that are all a parser might need to work with. So you can chop off a prefix of input and things like that. And then input parsers combines these two. Actually, I have slides all about that. So yeah, monoid subclasses comes with all of these. Input parsers builds on that, and parsers to export a bunch of type classes for building concrete parsers on. And then there's another branch. Let me go back. So rank 2 classes and deep transformations are kind of a completely different team. So rank 2 classes is a hard-kinded data library, which may have been the first, I'm not sure. It certainly appeared before that article that defined hard-kinded data. For you, well, does anybody not know what hard-kinded data is? Okay, cool. I can skip that part. Apart from the usual functor, foldable, traversable classes, it also defines some unusual ones, apply and applicative and distributive, which are all kind of mere images of the usual the type classes that work on the kind type. And logistic, which is, well, you could describe it that way, but it's just working with setters instead of getters, like functories. And there's the template Haskell module that can define splices for all these classes for usual records. And then grammatical parsers is a kind of culmination of these branches. Combines all that to produce, well, parser combinator library, but also grammar combinator library, because it expects parsers to be grouped in a bunch of productions. All these productions are packed in a grammar, which is just a record of these productions, and productions refer to each other. So what's the point of all that? Well, first of all, because mostly because of the distributive class, we can actually examine these productions and verify them and figure out how they refer to each other. And then there's this function fixed grammar, which takes self-referring grammar and packs it into a record of complete parsers. And that also allows us to memorize results of the parse at different points, and allows us to work with left recursive grammars, finally. Oh, and another interesting result is that this little expression here, for example, will take two grammars and OR them, which means basically you get a union of two languages described by the two grammars. So I applied grammatical parsers already on a few languages, Oberon, Modular 2, and Lua, and something else. And then I tried it on Haskell. Oh yeah, one more dependencies. So the hard-kinded data as a concept, all the libraries have a problem with nesting of records. So if the f parameter, the type parameter, appears twice on two different levels, you can't apply, for example, a map on it of the rank 2 type, because it would only transform the outer f, but the inner f remains there, and then it's unbound. So you get a type error. And of course, when working with compilers, abstract syntax trees are nested. So hard-kinded data is just not applicable there. That's also a problem with recursion schemes and probably other methods as well. And the issue is that natural transformations, which is what hard-kinded data libraries work with, must behave uniformly. So we transform all occurrences of P to Q. That is another problem. The solution for the nesting is to split up the parameter into two. I call them D and S for deep and shallow. So the outer parameter is the shallow type constructor, and all the subtrees are going to use the deep one. So that basically allowed me to replicate all the machinery of higher kind of data. Oh, yeah, so separate problem is that natural transformations must cannot look into the actual parameter A because it's for old. And sometimes you want to do different things to say patterns as opposed to expressions. So solution there, again, in the same library, deep transformations, is to use unnatural transformations and replace parametric with ad hoc overloading, meaning we use this constraint. This transformation at the type A can behave this way. And it, depending on A, can have different domains and codomains. And that complication also allowed me to implement attribute grammars in the library, which was pretty neat. Okay, so those are the dependencies, and then they let me build STs like this. So every node has a wrapper, and for example, once the tree is immediately parsed, every wrapper contains the start and end position of every node in the source tree. Then later there's environment for the bound identifiers, etc. But as you can see, that does so there's twice the number of objects in the heap compared to trees that grow approach, for example. Yeah, this is what this declaration would end up looking like. Oh, there's 4 type parameters in type of every node. That's lambda is the language of the node itself. L is the language of all the subnodes. D and S are the deep and shallow wrapper types. So yeah, it's all very idiosyncratic, and I don't actually expect anybody to contribute unless they're really masochistic. But still, you never know. These are the modules, and there's relatively few so far, especially compared to GHC, I guess. You may note that grammar does not directly depend on AST. Instead, there's, AST already stands for abstract syntax tree, but there's also further level of abstraction, which is the finally-tagless technique applied to AST. So the grammar invokes the abstract implementations, abstract class methods that build the AST, which allows the same grammar also to be used for different concrete AST types. So grammar productions from here, for example, which is outside the extensions module, so that's just Haskell 2010, are also reused to build the extended AST. Yeah, data flow is pretty simple so far. Source is parsed, identifiers are bound. Then based on this binding information, some nodes like infix applications may be reorganized when we find out what the fixity is, and then it may be reserialized back to the same source, or it can be pretty printed. Oh, and for pretty printing, I use template Haskell. So I just transform the AST into template Haskell AST, and then use template Haskell pretty printer. That was a convenient shortcut. And it also uncovered a lot of bugs in template Haskell pretty printer. So I said it's fairly small. Here's the numbers. And keep in mind, so all the extensions are described separately. I can show you in the source code a bit later. So if not for the modularity, it could have been much simpler, but it wouldn't be the point. There's a test suite that basically it's mostly, around 3,000 files from GHC test suite. That's just a portion of them, but I was just picking them as I went to test a particular extension. So what happens is there's a bunch of round trips. I parse a file, then I reserialize it, check it that it's exactly the same. Then I go through all the transformations and pretty print it. Then I parse it again. Then I pretty print it again, check that it's the same, etc. And so for these 3,000 source files, it takes 13 minutes or so. They're only positive tests, so I check that valid programs do, valid modules do compile. I don't check that invalid don't. That's future work. So some side effects of the project is, it forced me to improve the dependencies, and also discovered a bunch of issues in the GHC, mostly in the template Haskell pretty printer. They're all fixed. There's a bunch of documentation issues, mostly relating to explanation of the grammar and effects of different extension pragmas. Not quite all have been fixed. And so I'm not quite sure where to go from here. I'll certainly keep it up to date with the latest extensions. I heard about some that I haven't covered yet today. I may try to extend the compiler pipeline so it becomes an actual compiler rather than just a parser and pretty printer. Or I may concentrate on more like source level utilities. So I have a scheme where I what I call extension reformulators, where there's a transformation that takes source code and eliminates a particular extension and reformulates it in terms of others. Like I can do that for example, n+k patterns, because template Haskell doesn't support them. So in order to pretty print it, I have to lose them. And I think I reformulate them in terms of pattern views instead. So if I actually do that for more extensions, I may eventually get rid of most of them and just produce something close to core. And that would be a good, I guess, point to continue with type checker or something. But this is my background work, like weekends mostly, so don't expect it anytime soon. And that's it. Thank you.
Really cool work, and I'm really amazed that you were able to sort of break down the grammar so composably. It would be really cool to see a static extension.
Okay.
And this explains a lot of the sorts of tickets that we've been hearing recently. I now understand. A quick comment. You actually don't give yourself enough credit, I think, when it comes to your heap usage. GHC's TTG actually has a very similar effect with xrec, which introduces a box in between every.
Yeah, no. Yeah, I have a problem. I can't show both screens at the same time. So no, that's fine.
Okay.
I just you asked for the source code, so.
But yeah, so I think that doubling is also something that GHC exhibits. Regarding the name, there is work underway currently to refactor GHC's parser to make it and AST.
What happened now?
To factor it into a separate package. The name of that package is yet to be determined as well. Yeah. So we can have a language.
I'll try.
Yeah, language GHC Haskell would be another good name for GHC's variant. We can, I don't know, have a thumbware or something with the name, I guess.
Sure.
But yeah, that's.
Oh.
And
how do I maximize this?
Question if there is one in there, I guess. I can't remember.
Oh
no.
Well, you wanted to see some extensions on how they're implemented. Right. So there's these, I don't know, standalone deriving strategies.
Like a syntax or something, I don't know. Yeah, okay, yeah.
Yeah, so this is like, I don't know, deriving via mixin. Sorry about the lines. I can't figure out how to maximize Emacs because...
how many extension points are there?
Oh... 94.
Okay. Yeah.
Some are combinations of two different extensions because there are some unexpected interactions. I tried to replicate GHC's behavior. Yes, Leonard?
So I have two questions. So first you said you resolve operator precedences. So
yes.
So that means you have to do import processing.
Yes. Yeah.
Okay. The other question: how do you deal with the funny layout rule in Haskell?
Oh.
The one that says that if you get the parse error, you should insert the right.
So I have a different approach than described in the standard. This is basically it.
Well, I can't read the thing.
Yeah, sorry. I
You
can,
could just
yeah, so this is basically the function that does it.
I think it's better to...
Well, we can take it offline, perhaps, but yeah.
we can take it offline. I also had a comment on your lines of code for the different parsers.
Yes.
So micro Haskell has 450 lines in the lexer and 900 lines in the parser.
That's cool.
We'll switch to...
Okay. Sure.
Well, we can have one more question or two more at once while we set up next speaker.
Yes.
Is it a full concrete syntax tree with white space, and would it be like easy for me to do like source transformations?
Yes, the parsed syntax tree contains complete information to reconstruct the source code.
With the comments?
With the comments and white space and all positions, yes. Yes?
So a lot of projects use GHC lib parser, for example, for like,
Yes.
Is the goal of this project to be like to achieve parity with that?
Doesn't depend on libGHC at all,
Right.
So yeah.
Is it likely to achieve parity with this? Okay, could I like swap in GHC lib parser with this?
Well, at the AST you get won't be the same, obviously. So in that sense, no. But I mean, it could use for some of the same purposes.